Expression is an expression that contains a radical, and that's like a square root sign. That looks horrible. Oh, that's way too big. Okay, and most commonly you see a square root, but there's other kinds of roots. There's cube roots, fourth roots, fifth roots, sixth roots. If it doesn't have a number, it's a square root. A cube root would look like this. It would have a little number on there. Okay, so but we're not worrying about cube roots right now, so I just wanted you to recognize what the difference is. So if I have a radical expression, whatever is underneath the radical is called the radicand.
Radicand?
Radicand, yeah.
Radicand.
Okay, so a radical expression contains a radical, and whatever's under the radical is called a radicand. Now, for a radical expression to be in simplest form, you have to have three things. Okay, your radicand can't have any perfect square factors. Yeah, radicand, like radicand, but with a D on the end. There cannot be a fraction under the radicand, and you cannot have any radicals in the denominator. Basically, what this is stating is that if you have two numbers that are non-negative, and it has to be non-negative because we don't take the square root of negative numbers at this level. If I have the square root of 50, that is equal to the square root of 2 times the square root of 25. Or if I have the square root of 3 times the square root of 27, that will give me the square root of 81. So I can either take, sorry, that shouldn't pop up. I can either take a single one and break it into 2, or I can take 2 and put it together to make 1. And I do whichever makes the most sense for what I'm trying to accomplish. Yay. There's two methods. The first method is just having all your perfect squares memorized and knowing what goes into what. Everybody got that? Perfect squares all memorized and you guys all know? No? I didn't think so. That's okay. Second method is to make factor trees.
So we're doing gardening now. Math gardening.
Okay. I make my factor tree. 80 is 2 times 40. 40 is 2 times 20, 20 is 2 times 10, and 10 is 2 times 5. Every pair of matching numbers is a perfect square.
So we get 2 perfect squares?
So we have 2 perfect squares. These numbers come outside of the radical. Any number that is not in a pair is like a remainder.
So does that go
it stays inside. So this is like a remainder. Oh, I don't want to write that big right there.
So is the last one the remainder or no?
Whatever is not in a pair.
But if you broke it down as 4 times 10 instead of 2 times 20 or 40.
Then I would have done 4 times here, right here, 4 times 10. Then 4 is 2 times 2, and 10 is 2 times 5. I would have okay. There's this thing called the fundamental theorem of arithmetic, and the fundamental theorem of arithmetic states that every number has a unique set of primes. So if you factor it, it doesn't matter how you start the breakdown, you'll get the same set of primes every time. So no matter even if I did 80 was 8 times 10, when I finished breaking it down, I would have still had 2 pairs of 2s and a 5. So these are perfect squares.
So 5 doesn't have anything.
5 doesn't have a match, so anything that doesn't have a match stays inside. Anything that does have a match, you bring it out. Now you'll see I have 4 2s here, but each one of these is a perfect square, so I bring 1 per pair out.
They can be perfect squares even though they don't come from the same number.
Yeah, okay, so basically, taking the side up here, 80 is equal to, if I multiply all these together, that's 16 times 5. And the square root of 16 is 4. This is just an easier way to do that, because if you didn't know that 80 was 16 times 5, I have 2 pair. I bring out 1, 2 for each of the pairs. I multiply those back together, and the remainder stays underneath. So let's do it with 54, and I'm going to kind of come out to the side a little bit on this one because we're a bit close. 54 is 2 times 27. And 27 is 3 times 9. And 9 is 3 times 3. I have a pair of 3s. And then I have 2 numbers that don't have anything that goes with them, right? So I'm going to bring out that 3. And I'm going to leave the 2 and the 3 that didn't match up to anything behind. And so my answer is going to be 3 times the square root of 6. So these get left behind, these remainders get left behind inside. You can only get to come out if you're with a pair. So every pair, 1 comes out. Want to see another one? Hold on a second. What times what will make 180?
90 times 2.
Okay, that works. And 90 is?
Or 45 times 4.
Well, yes. But let's do 90 now.
Or we can't 30.
30
times 3.
Okay, we'll do 30 times 3. Actually, you know what? I'm going to write that the other way. And 30 is?
15 and 2. Or 10 and 3.
And 15 is?
7.5 times 2. Oh, 3.
3 times 5. No decimals. All right, here I have a pair of 3s. And here I have a pair of 2s. Okay, guys, I'm recording. Okay, so I have a pair of 3s and I have a pair of 2s. For each pair, 1 comes out. So I have a 3 and a 2. And I have a 5 that's left behind because it didn't match up with anything. Now you'll notice I'm ignoring every number that I split because 90 was 3 times 30, so 90 is taken care of here. And then 30 is 15 times 2, so 30 is gone. And then 15 is gone from the 3 and the 5. You only take the end of the branches. Okay, so 3 times 2 is 6 times the square root of 5. So 180, sorry, the square root of 180 is actually equal to 6 times the square root of 5. These two things are the same.
Ooh, I have one for the next one.
Go ahead.
128 is 4.
Okay. And 4 is,
219.
and 128 is,
64 and 2.
and 2, or 64 is,
8 and 8.
8 is,
4 and 2.
and
2, 2.
2, 2. 2, 2. We found 1 and 2, 2.
all right, so let's do pairs. I have a pair of 2s,
2, 2.
and I have another pair of 2s, and another pair of 2s, and another pair of 2s,
Oh, jeez.
and I have 1, 2 left behind. Do you see that?
I'm about to roll.
So I've taken care of all the ends of the branches. So I have 1, 2, 3, 4 pairs.
4 2 2.
So 4 2s come out, and 1 gets left behind. So 2, 4, 8, 16.
And another 2.
By the way, 14 doesn't have any perfect squares in it. 14 is just 2 times 7, so it does me no good whatsoever to have a 14. And 2 is just 2, so I can't take the square root of that either. So what I can do is I can multiply these together, and this is the same thing as the square root of 2 times 14, which is the square root of 28. And then 28 is 4 times 7, and 4 is 2 times 2, so I have that perfect square pair.
Yay.
So I can bring that out.
The 2 become 1.
That's a good sign.
They don't really become 1. What you're doing is every pair is a perfect square, and so you're taking the square root of it.
No, I meant the 2 square roots.
Oh, these two. Yes, those two become
the
1.
same square
Yes,
root.
absolutely, yes.
The 2 become 1.
So this would be what? The square root of
2 2. What?
What? 5 times 10?
5 times 10, which is 50. And 50 is,
25
and 25 is,
5 5.
and hey, looky there, there's another perfect square pair.
2 2.
So that's the point of putting them together, is because individually I can't do anything with either of these, but when I put them together, there's a perfect square I can pull out. Same here. Individually, I can't do anything with a square root of 5 or a square root of 10, but a square root of 50 has a perfect square in it, so I can pull it out. Now let's throw in variables. Okay. Before we do this one, I want to just show you, let's say I do x squared. The square root of x squared is going to be x. If I have x to the third, there are 3 x's here, right? So I have a pair and 1 left over.
So would it be an x on the outside
with 1 on the inside. X to the fourth, x to the fifth would be x squared times the square root of x. Do you guys see a pattern?
Yep.
Wait, let me write the pattern.
We're going to divide the exponent by 2. Okay, whatever answer that is, this becomes the exponent outside. And if there's a remainder, which would always just be 1, stays inside. So for example, if I have the square root of 27, x to the 27th, I'm going to divide 27 by 2. 27 divided by 2 is 13, remainder 1. So the remainder stays inside. Does that make sense? So that's how you deal with the variables. We just divide the exponent by 2, and if there's a remainder, it stays inside. So now, when you see something like this, you only have to factor the number portion. 90 is 2 times 45, which is 5 times 9, which is 3 times 3. I have a square root pair, or perfect square pair.
And then the 2 5.
So I'm going to bring that 3 out. I'm going to leave some space for my variables, and I'm going to put the 2 and the 5 inside. Okay. Now x to the third, if I divide it by 2, I get x with a remainder of x, right? Does that make sense? So 1x comes out, 1x stays in. Y to the fourth, if I divide it by 2, it divides evenly. and I have 2.
But none on the inside.
None on the inside because it divided evenly. And then z to the 5th, if I divide by 2, I get 2 remainder 1. Let me first factor the number. Let's start there. Okay. So 32 is 2 times 16. 16 is 2 times 8. 8 is 2 times 4, and 4 is 2 times 2.
So you get like a 2 on the outside and a 2 on the inside. Because one of the 2's is by itself.
I get 2 2's outside.
And 1 on the inside.
Mm-hmm. Okay, so 2 2's came out, 1 gets left behind. Any questions about that part?
Or we could make it a
K to the 4th. 4 divided by 2. So I get 2 K's. T to the 5th. 5 divided by 2. 2 with a remainder of 1. So the 2 comes out, the remainder of 1 stays in. So all the remainders just stay inside. And that's always the case. Here I have a remainder, so that stays inside. Here on the exponent I have a remainder, so it stays inside. Does that help? Okay. So then after I've figured all that out, I'm going to multiply this stuff that needs to be back together. So I get 4r k squared t squared times the square root of 2t. And that's my final answer there. That's completely simplified. Okay, 56 is,
28, I think.
that's correct, 2 times 28. 28 is 2 times 14. 14 is 2 times 7. 1 pair of 2's. So a 2 comes out, and a 2 and a 7 stay behind because they didn't have anything to go with them, right? Well, x to the 1 does not even divide by 2, so it just stays in there. Did you guys see that? Y to the 10th, 10 divided by 2 is 5. And then z to the 5th, so 5 divided by 2 is 2 with 1 left over. So this part out here is good, so I'll just write that over.
And then on the inside it's
14xz. And the quotient property square roots is this, I had to make, oh, okay, for any non-negative, again, so they have to be non-negative real numbers. If I have a fraction underneath the radical that is the same thing as a radical over a radical, or if I have a radical over a radical, it is the same thing as a fraction under the radical. Now, the square root of 36 over 25 is the same thing as the square root of 36 over the square root of 25. These are both perfect squares. So I can take the square root of 36 and the square root of 25, and I'm simplified. Okay? The square root of 50 over the square root of 2, neither of these are perfect squares, so it makes actually more sense to put them together. So we can go both ways, right? I can take it apart if that makes more sense, or I can put it together if that makes more sense. Now the square root of 50 divided by 2 is the same thing as the square root of 25, which is 5. So see here, it makes more sense to take them apart. Here it makes more sense to put them together. Sometimes we have to look at things and say, okay, well, that's not a perfect square, that's not a perfect square. But what would happen if I divided both of these by 2? I simplified that fraction. In which case, I can then split it, and I get 7 over 4. So here I divided both of these by 2 to simplify the fraction inside first and then split it. Back to the very first page of the note packet, and I said you can't have any radicals in the denominator. And sometimes it doesn't work out nicely like these to where you don't have a radical in the denominator anymore, and you have to do what's called rationalizing the denominator. And that's the process of getting rid of the radicals.
What's that, undenominated?
In.
And,
Yeah. The first thing I want to do is I'm going to look at 35 and 15. Neither of these are perfect squares, right? And so there's no point in splitting this at this point. So then I'm going to look at, do 35 and 15 have anything in common?
Yeah.
What's that? 5. So I'm going to go ahead and divide by 5. And that's going to give me the square root of 7 over 3. Now, when this happens, I can't leave a fraction. The second thing on the list was you can't have fractions under the radical, right? So I'm going to go ahead and split that. Now I no longer have a fraction in the radical. But I have a radical in the denominator, which I'm also not allowed to have. So I'm going to take that square root of 7 over the square root of 3. And to get rid of a square root of 3, I'm going to multiply by a square root of 3. Because if I square a square root, it goes away. And so to square it, I multiply by itself, right?
yeah.
And so then what happens is, this becomes the square root of 21. And technically, I guess you could say that becomes the square root of 9, but we can skip that step. And it becomes the square root of 21 over 3. Because these two things cancel the radicals out. A radical times a radical of the same number just gives you the number. No, this is your answer here. Okay, so I want to get rid of this radical 12 in the denominator. I'm going to multiply by 12 over 12. So 6 times 12, 72. And I can simplify that 72. 72 is 2 times 36, and 36 is 6 times 6, right? So this becomes 6 times the square root of 2y over 12. And 6 over 12 will reduce. So this becomes the square root of 2y over 2. Now, this 2 and this 2 don't reduce. You cannot reduce a number inside the radical with a number outside of the radical. They have to either both be inside or both be outside. Okay, so this is done. You can't reduce it any further. 45 tenths, you want to reduce it first or second?
Reduce.
Okay, so these will both divide by what? Yeah, these will both divide by 5. So that gives me 9 halves. So that's the square root of 9 over the square root of 2. And the square root of 9 is 3. And so that looks like it would be pretty, right? But it's not, because you can't have a square root of 2 in the denominator. So I'm going to multiply by the square root of 2. And the square root of 2 times the square root of 2 is just 2.
So that's okay.
So this is your final answer here.
Oh, cool.
Completely simplified. If I have multiplication and I have fractions under the radical, I want to do that multiplication first. Okay, so this is going to give me 35 over 6. This won't reduce. So I'm going to do the square root of 35 over the square root of 6. Then I multiply by the square root of 6 over the square root of 6, which gives me a denominator of 6 and a numerator of, let's see, 0, carry my 3, 210, right? Did I do that right? 18. Yeah, that's correct. Okay, so 210. Now, I'm going to factor 210 just to see what happens, to see if there's any perfect squares in there. I think that there aren't, but I'm going to double check myself. So that's going to be 105, which is going to be 5 times 21, which is going to be 3 times 7. No pairs. Right? No pairs, nothing comes out, so this is done. Conjugates occur when you have expressions and one's a plus and one's a minus. And those are conjugates of each other. So for example, if I had x plus 2, the conjugate of x plus 2 would be x minus 2. These are conjugates. Or if I have 3 plus the square root of 2, the conjugate of this would be 3 minus the square root of 2. So they look the same, except one's a plus and one's a minus. So we have to use conjugates sometimes. Here's the nice thing about conjugates. Let's say I take these two conjugates here. And I multiply conjugates together. Watch what happens. I do my first, and I get 9. I do my outside, right, FOIL. Do you remember FOIL? And I get minus 3 times the square root of 2. And then I do my inside, and I get plus 3 times the square root of 2. And then I do my last, and I get minus 2. Excuse me. And look at this. Minus, plus. Those go away. Multiplying conjugates together. Multiplying. There's no y in multiplying, huh? No, yeah, there is. I don't know how to spell multiplying. Anyway, multiplying conjugates.
No, because you take out the y and add ing, right? Isn't that how it goes?
Not for multiplying. I can't spell today. Multiplying conjugates eliminates
That's weird.
square roots. And you know how we can't have a square root in the denominator? Well, if I have something in the denominator that's an expression, if I just multiply this by the square root of 2, I'm not going to get rid of any square root because the square root of 2 multiplied by here will go away, but then I'll just have 5 times the square root of 2 plus 2. All I'll have done is shift it over. Does that make sense? Do you guys want to see what I mean? Anybody? Can't just multiply by the square root of 2. All it would do is shift the square root of 2 off of this and over to here. I have to get rid of the square root in the denominator. So to get rid of the square root in the denominator, I multiply by the conjugate. With a J, not a G. So instead of I've got 5 plus the square root of 2. So I'm going to multiply by 5 minus the square root of 2. Okay? And what will happen is my numerator is going to have to be distributed, or possibly FOILed if there's an expression in the top. My denominator is going to end up being 5 times 5, the square root of 2 minus the square root of 2, because these in middle terms go away. So you don't have to FOIL the whole thing, because the middle terms would disappear anyway. Multiply the first, multiply the last. And you get 25 minus 2. So this is going to be 15 minus 3 times the square root of 2 over 23. The only way you can reduce at this point is if this number, and this number all reduce by the same thing, like a triangle. 15, 3, and 23 don't have anything in common, so they don't reduce, so you're done. What would be the conjugate here?
2 plus the 2,
Not plus, always the opposite sign. So if it's plus, you multiply it by minus. If it's minus, you multiply it by plus. Okay? Which is going to give me multiply the first, multiply the last. So I'll have 4 minus 2. And then distribute the numerator. So I have 6 minus 3 times the square root of 2 over 2. And again, that won't reduce because this whole triangle here would have to reduce by the same number, and they don't. Okay, so my conjugate on the bottom here.
So the one on the top, the
3
one on the
plus
bottom.
So 3 plus root 7.
Mhm.
So that gives me 7 times 3 plus the square root of 7. And then remember, because I'm conjugates, I can just do first and last. And that only works because I'm doing conjugates. So I get 9 minus 7. So I get 21 plus 7 root 7 over 2. And again, 21, 7, and 2 do not all divide by the same, so I can't reduce. Adding and subtracting radical expressions is just like terms with variables.
Oh, wow, you did cursive in the number. That's kind of cool.
The radicals must match. Okay, so if we look at this first radicals, the whole thing. Radicand is just the number underneath. If I look at these are all root 2, correct? So what I do is I take those numbers that go in the front and actually add and subtract them. So 5 plus 7 is 12, minus 6 is 6. Just like terms. Nothing happens to the square root. It stays exactly the same. You just add and subtract the number out front. If there is no number out front, it's a 1. Just like with an x, if there's no number on the x, it's a 1. It's the same thing. They act just like variables. So Sometimes it's helpful to rearrange them and put the ones that match together. So I've got 2 of these that have root 7 on them. And 2 of them that have root 11 on them. Add the 2 that match together. 5 minus 6 is -1. So you just treat them just like a normal variable. All right, so here I have 2 like terms and 2 that don't go together. So I'm going to combine the 2 like terms. 10 and 5 is 15. 15 root 5. And then the other 2, they don't go with anything, so you just leave them there. They just hang out. We have to simplify them. So to simplify them, I do the factor tree thing. Okay. The part that comes out gets multiplied times what was already there. So that 4 was already there, and I add the 3 from the pair. And then the part that stays inside just stays inside. So this becomes 12 root 6. So 4 times the square root of 54 is the same thing as 12 times the square root of 6. And then I'll try 24 is 2 times 12, and 12 is 2 times 6, and 6 is 2 times 3. And here's my matchy.
So it's 4.
2 times 2, 2 times 3. So 4 times the square root of 6. Now they match? Yeah. So now I can add them.
Would it also work as 16?
We try to make them all matchy-matchy. So 18 is 2 times 9, which is 3 times 3. So this becomes 2 times 3 times the square root of 2, because those 3's come out. 32 is 2 times 16, which is 4 times 4, which is a pair. I don't have to split it any further than that. As soon as I find a pair, I can stop.
So instead of doing 2 times 8?
Mm-hmm. So this is going to be 2 times 4 times the square root of 2.
And then just the 72.
And 72 is 2 times 36, and 36 is 6 times 6.
Question. With that one, would that be like a variable within the front part? Or would it be
There's
more?
nothing in there. It's like a 1, yeah.
Yeah, a 1.
It's a little invisible 1. So I have 6 times the square root of 2 plus 8 times the square root of 2 plus 6 times the square root of 2, and that gives me 20 times the square root of 2.
Mm.
All right, 45 is 5 times 9, and 9 is 3 times 3. So this first one becomes square root of 5. 20 is 4 times 5, and 4 is 2 times 2. So this becomes 2 times the square root of 5. And 245 is 5 times 49, which is 7 times 7. So it becomes 7 times the square root of 5. And that same thing as 9 root 5 plus 2 root 5.
Negative?
Oh, yep, negative, thank you.
Yeah.
See, even if you've been doing it for 30 years, you still can make mistakes. So 9 plus 2 is 11 minus 7. So I get 4 root 5. Equals is 3 times 2 and 2 times 6. So 6 root 12. Now, 12, I need to see if I can simplify. So I'm going to do 3 times 4, and 4 is 2 times 2. And there's a pair in there, right?
So it becomes like 12 square root 3.
Uh-huh. So it's 12 root 3.
It's kind of like the 12 became.
So I'm going to multiply the outside numbers. I'm going to get 99. And I'm going to multiply the inside numbers, and I don't know that one off the top of my head, so I'm going to actually...
Does that look like 75?
Okay, so I get 99 times the square root of 75. 75 is 3 times 25. And 25 is 5 times 5. So I'm going to get 99 times 5 root 3.
Okay, Renata, use that calculator.
And since I don't know what 99 times 5 is... No, I already did it.
She beat you.
She beat me.
So I get 495 root 3.
It's kind of worrying if you were going to...
This acts just like normal distribution, so I'm going to take this 3 times the square root of 5, and I'm going to multiply it by each of these individually.
Foil?
No, not FOIL, because it's just 1.
Dish.
Yeah.
Dish.
So it's going to be 3 root 5 times 2 root 5 plus 3 root 5 times 5 root 3. So I multiply by each. I'm distributing. So that gives me 10 times the square root of 25.
Jeez.
And this gives me 15 times the square root of 15. Now
Jeez.
25 is 5 times 5.
Where'd the 10 come from? I thought there
Sorry,
was...
6.
Yeah, I'm like, where'd the 10 come from?
Okay, 6. So 25 is 5 times 5, right? So I can pull that out. So that becomes 6 times 5. 15 is just 3 times 5, so nothing can come out. So this is 30 plus 15 root 15.
Woohoo.
And these are not like terms, so can't add any further.
Wait, let me write this.